In this video, we are looking at activity 6B, which is ideal gas law problems. And so the ideal gas law is on your formula sheet. It's PV equals nRT. P standing for pressure, V being volume, N being the number of moles, R being the ideal gas constant, which is also on your formula sheet. But I'll go ahead and write here for you. 0.08206 liters times ATMs over Kelvin times mole, and then T being temperature. And so just a little bit about R, the ideal gas constant. There are various units in which you can get the ideal gas constant, but the one that you are given on your quizzes and tests in chemistry class is in liters times ATMs over Kelvin times mole. So when you do your problem, you need to make sure that the units that you are using for your pressure, volume, and temperature and your number of moles match the unit given in the ideal gas constant. So if your volume is initially in milliliters, you need to convert it to liters before you use PV equals nRT. If your temperature is given in degrees Celsius, then you need to convert it to Kelvin before you use the ideal gas law. So just something to note moving forward. Let's start with number one. It says, how many moles of gas does it take to occupy 120 liters at 2.3 ATMs and 340 Kelvin? So I always like to write out all my variables. So I write P, V, N, and T. I don't put R because R is going to be the same every time, but if you want to write out R each time, you can if that helps you. So how many moles? So I know I'm going to be looking for moles. That's in, so I'm going to put a question mark there. Does it take to occupy 120 liters? Liters is a unit of volume, and that matches the liters that's in my ideal gas constant, so I don't need to do any unit conversions there. So 120 liters at 2.3 ATM. ATM is a unit of pressure, and that's the correct unit of pressure to match my gas constant. So I'm going to go ahead and put 2.3 ATMs, and then 340 Kelvin. So that's my temperature. So I have all the correct units to match the units in the ideal gas constant. So all we need to do is substitute into our equation. So instead of setting the equation equal to PV, we need to solve the equation so that N is on the side by itself. So PV equals nRT. If we want to get N by itself, we need to divide by R and T. So R cancels, T cancels, so we're left with N equals PV over RT. And now all we need to do is substitute in. Pressure is 2.3 ATMs. Volume is 120 liters. The ideal gas constant is 0.08206, and the units are liters times ATM over Kelvin times mole. Put all that in parentheses. And then our temperature is 340 Kelvin. It's supposed to be a capital K. Wasn't my best one. Okay, so we just need to plug these numbers into our calculator, and then let's look at our units. So we have ATMs, which will cancel with the ATM on bottom. Liter will cancel with the liter on bottom, top. Kelvin, we have one in the numerator and one in the denominator, so those will cancel out. And we're just going to be left with units of moles, which makes sense because we were looking for N. So now let's plug this in, literally plug into our calculator. We have 2.3 times 120, hit enter, and then I'm going to do divided by, and I'm going to put my denominator in parentheses, 0.08206 times 340, close parentheses, hit enter, and I got 9.89. Looking at significant figures in my values, I see that this has 2, 2, and 2 significant figures. I'm going to round my answer to 2 significant figures as well. So I'm going to round to 9 point, and then if we have 8, 9, if we want to round to 2 significant figures, then 9 is going to make the 8 round up. So this is approximately 9.9 moles. We'll box that first answer in there. looking at number 2, it says, if I have a 50-liter container that holds 45 moles of gas at 200 degrees Celsius, what is the pressure inside the container? And so here, the first thing that I am noticing is that we have degrees Celsius, not degrees Kelvin. So we do need to make sure that we convert into degrees Kelvin. But the rest of our variables seem correct. We have moles, we have liters, and then it's asking us to find pressure. So our pressure will come out in units of ACMs. So let's write out our variables, P, V, N, and T. Pressure, of course, is what we're trying to find, so we'll put a question mark there. Volume is 50 liters, right here. The number of moles, 45 moles. And then the temperature is 200 degrees Celsius, so we need to convert that into degrees Kelvin. So we do that just by adding 273. So Kelvin equals degrees Celsius plus 273. So let's do 200 plus 273 would give us 473. So we're going to put 473 Kelvin down here. Now we have everything we need to solve. We just need to rearrange our equation to solve for P. So PV equals nRT. All we need to do is divide by volume to isolate P. Volume cancels. We have P equals nRT over V. And I'm going to move this up here. So substitute N. So we have 45 moles times R, the ideal gas constant, so 0.08206 liters times ATM over Kelvin times mole times T, 473 Kelvin. And then all of that is over our volume being 50 liters. So let's look at our units first. So we have liters on top, liters on bottom, those will cancel out. We have moles in the denominator and moles in the numerator, so the moles will cancel. And then we have Kelvin in the numerator and Kelvin in the denominator, so our Kelvin will also cancel out, which just leaves us with ATMs, which does make sense because we were looking for a pressure. And ATMs are a unit of pressure. So let's get our calculator out, plug this into the calculator. We have 45 times 0.08206 times 473. Get that answer and then divide by 50. And we got 34.93. So equals 34.93 ATMs. But we do need to look at our significant figures in our values. So we have 1 here, 2 here, and 1 here. So we want to round to just one significant figure. So this is kind of a big round, but we need to round just to this first place, and the 4 will cause us to round down to 30. So this is approximately 30 ATMs. And we'll box in that final answer. Number 3. Number 3 says that it is not safe to put aerosol canisters in a campfire because they can explode. If I have a 1 liter canister that holds 2 moles of gas and the campfire is 1400 degrees Celsius, hot campfire, what is the pressure inside the canister? So let's write out our variables. We have P, V, N, and T. Let me move this up so you can see a little better. Our pressure, it says what is the pressure? So that's what we're looking for, so we'll put a question mark there. It says we have a 1 liter canister, so that is our volume, 1.0 liters, and that is in the correct units for our value of R, which I'll go ahead and write out because you can't see it at the top anymore. So it's 0.0826 liters times ATM over Kelvin times moles. So liters is the correct unit. Now for N, it says we have 2 moles of the gas, so 2 moles. And then we have 1400 degrees Celsius. So degrees Celsius, we need to convert to Kelvin. So we're going to do 1400 plus 273, which will give us 1673 degrees Celsius. Sorry, not degrees Celsius anymore, 1673 Kelvin. Okay, so now that we have all of our variables, all we need to do is solve for P. So if we have PV equals nRT, and we want to solve for P, we just need to divide by V on both sides. So P equals nRT over V. So we're once again going to come on up here to substitute in our numbers. So N is 2 moles, R is 0.08206 liters times ATM over Kelvin times mole. And T, of course, is 1673 Kelvin. Okay, and all that is over our value for volume, which is 1.0 liters, which makes it very easy because anything divided by 1 is going to be the same thing. So moles in the numerator cancels with moles in the denominator. Kelvin in the numerator cancels the Kelvin in the denominator. And liters in the numerator cancels the liters in the denominator. We're just going to be left with ATMs, which does make sense because we were solving for pressure, P. So let's plug this into the calculator. So we have 2 times 0.08206 times 1673, and that gives us 274.57 divided by 1. That's going to be the same thing. So our answer was 274.57, but we are going to need to round that value. So this is a number of ATMs. But looking at our problem, we have 2 sig figs here, 1 here, and 2 here. So I technically need to round to 1 significant figure here. So I'm going to round to this first significant figure. So approximately the 7 will make that round up to a 3. And then I'm going to fill in zeros as placeholders. So 300 ATMs is my answer with 1 significant figure. This next problem, how many moles of a gas are in a 3,000 milliliter scuba canister if the canister is 26 degrees Celsius and at 200 ATMs? So let's write out our variables, P, V, N, and T. I'm going to go ahead and rewrite the ideal gas constant R at the top. R is equal to 0.08206, and then the units are liters times ATM over Kelvin times mole. So I'll write that up there so we have that as a reference for ourselves. So it says how many moles. So we are looking for N, number of moles, are in a 3,000 milliliter scuba canister. So we need the units for our volume to be in liters. So let's go ahead and convert 3,000 milliliters to liters. So 3,000 milliliters, we'll use a little dimensional analysis here. Milliliters always goes on bottom, so it will cancel. Liters goes on top. And we know that there are 1,000 milliunits in one base unit. Or if you don't remember that, just write out your King Henry died by drinking chocolate milk chart to figure that out. So 3,000 divided by 1,000 is going to give us 3 liters. So our volume is 3 liters. Okay, so 3,000 milliliters, we've used that. If the canister is 26 degrees Celsius, so we don't want our temperature in Celsius, we want it to be in Kelvin. So we need to convert to Kelvin by adding 273. So 26 plus 273 is going to give us, get out my calculator here, because I'm not feeling very confident on my mental math right now. 26 plus 273 gives me 299. And that is Kelvin. So let's put 299 Kelvin. And then last but not least, it's at 200 ATM. So my pressure is already in the right units of ATM. So 200 ATM. And now we just need to rearrange our equation to solve for number of moles. So PV equals nRT. We're going to divide by R and T, divide by R and T. So do that on both sides. R cancels, T cancels. So we have N equals PV over RT. Now we just need to substitute numbers in. So pressure is 200 ATM times volume, 3 liters, over R, 0.08206 liters times ATM, over Kelvin times mole, times our number of moles, or times our temperature, which is 299 Kelvin. So now all that we need to do is plug this into our calculator. 200 times 3 divided by, put in parentheses, 0.08206 times 299. Close parentheses, hit enter, and that gives us 24.45. And so looking back in our problem for our sig figs, we have 1 sig fig here, 1 here, and 2 here. So we only need 1 sig fig in our answer. We're going to round that value to 20, and then our units, we forgot to look at that. ATMs cancels, liters cancels, Kelvin cancels, so our units are moles, which is indeed what we were looking for. 20 moles is our value of N. Our last problem says, I have a balloon that can hold 100 liters of air. If I blow up this balloon with 3 moles of oxygen gas at a pressure of 1 atm, what is the temperature of the balloon? Okay, so let's write out our variables, P, V, N, and T. It says, what is the temperature of the balloon? So we'll put a question mark there. My balloon can hold 100 liters of air. It's already in the correct unit, liters, so we'll put 100 liters. I blow up the balloon with 3 moles of oxygen, so 3.0 moles is our value for N, and a pressure of 1 atm, 1.0 atm. So all we need to do is solve for temperature. Everything is in the correct units. So PV equals nRT. And we can rearrange this equation to solve for T by dividing by N and R on both sides. N cancels out, R cancels out, so we end up with T equals PV over NR. So now all we need to do is substitute in our numbers. So let's move up here. Our pressure is 1.0 atms. Our volume is 100 liters. Our number of moles is 3.0 moles. And then our value of R is 0.08206 liters times atms over Kelvin times mole. Close those parentheses, draw my line a little longer. Now we just need a calculator. Oh, but first let's look at our units. ATM cancels with ATM, liters cancels with the liters down here, moles in the numerator cancels with moles in the denominator, so we will just be left with Kelvin, which is indeed a unit of temperature. Straighten that out a little bit, get our calculator out. So we have 1 times 100 on top, that's easy, and then divided by the stuff on the bottom, which is 3 times 0.08206, close my parentheses, and hit enter. So this gave me 406.2068, and this is in Kelvin. But we want to double check in the problem and make sure it doesn't specify what units of temperature we need. It just says, what is the temperature of the balloon? It doesn't specify whether it needs to be in degrees Kelvin or degrees Celsius, so we can go ahead and leave it in degrees Kelvin. But sometimes problems will specify that what is the temperature in degrees Celsius, in which case you would need to convert this back to Celsius by subtracting 273. So let's do both things, and we'll just put both answers here. We have 2 sig figs here, 1 here, and 2 here. So technically we just round to one significant figure. So it's approximately 400 Kelvin, which also is going to equal 400 minus 273 will give us our degrees Celsius. So let's do that real quick. 400 minus 273 gives us 127 degrees Celsius. So our temperature is 127 degrees Celsius or 400 degrees Kelvin. And of course we would want to round this value for Celsius to appropriate sig figs as well. So we technically would have to round to just 100 degrees Celsius, which, as you can see, that's a really large round. So let's just keep it in Kelvin and stick with that answer right there.